This is the second video of Chapter 9. We'll be talking for the next few videos about nucleophilic substitution. But before we get into more detail, we need to figure out what are nucleophiles and categorize them so that we can keep all of this stuff straight. So, if you would please reread section 9.1, pages 322 to 323. First of all, what is a nucleophile? So basically a nucleophile has to have a lone pair of electrons. So here are some examples. Water. Good old water is a nucleophile. Turns out it's not a really great nucleophile, but it's pretty good, and it has two pairs of electrons. That's fine, as long as it has at least one. Here's another one, hydroxide, which is the conjugate base of water, but it's also a nucleophile, and it's a much better nucleophile, as it turns out. We'll find out why later on. Here's another one, ammonia. Here's another one, the acetylide anion that we learned about way back in the alkyne chapter. Methanol, or generally alcohols, have two pairs of electrons. Don't forget, ammonia has one pair of electrons, acetylide ions have one pair of electrons, but again, it only has to have one. And then here's another one, iodide, which seems strange because it's going to be replacing a halide. That's what nucleophiles do, is replace halides, and yet it is itself a halide. That's true, it is. It has four pairs of electrons, but again, it only has to have at least one. Now notice that some nucleophiles are negative, as these three are. Some nucleophiles are neutral, as these three are. So here are some negative nucleophiles. I've just listed out some compounds here. Potassium iodide, sodium hydroxide, potassium cyanide, sodium acetylide of various types where the R group could be different things, sodium ethoxide, so this is an ethanol in which the hydrogen has been taken off, and so it's a negative oxygen and a positive sodium, just written as sodium ethoxide. Here's potassium hydrogen sulfide and potassium methyl sulfide. So these are ionic compounds. Notice each of these has potassium or a sodium. So looking at each of these formulas in turn, I would ask you to consider what is the anion and what is the cation. And once you figure out what the anion is, that's the actual nucleophile. So it's a positive thing and a negative thing, and it's the actual negative thing that's the nucleophile, as suggested by the fact that we're talking about negative nucleophiles. So take a minute and just write down what's the negative thing from each of these different ionic compounds. So now I will reveal the answers. So Ki, the negative is I minus. Sodium hydroxide, the negative is OH minus. Potassium cyanide, the negative is cyanide with a negative. Sodium acetylide ions, the negative is the acetylide anion with a negative charge. Now notice that when I write the pair of electrons there, these all have at least one pair of electrons, but for whatever reason it's just sort of traditional to write the dot dot for the acetylide anion. So the negative thing from the sodium ethoxide would just be the ethoxide with a negative oxygen. The negative of potassium hydrogen sulfide is the hydrogen sulfide ion, SH minus. And if it's the same thing but with a methyl instead of hydrogen, then it's the S-methyl. That's the negative thing. But this is a really important skill that hopefully you mastered way back in general chemistry, looking at an ionic formula, figuring out what's the positive thing and what's the negative thing. The important thing here is that it's the negative thing that's the nucleophile. Now we will see as we go through that sometimes the reagent over the arrow will be written as just the negative in a sort of net ionic way, and sometimes it will actually be written with the counter ion and not showing the negative charges, but you have to know what the negative charges are. So when a negative nucleophile substitutes for a halide, so the key here is that we're starting with an alkyl halide. That's the name of this chapter, is reactions of alkyl halides. So our X is the key molecule. It will be reacting with one of these negative nucleophiles. It will come in and replace the halide. The halide will leave with its pair of electrons to make it negative, and I've shown the pair of electrons there. Of course, it also has three other pairs of electrons, but the key is it's picking up a pair of electrons from that pair right there, and the nucleophile is going to share its pair, and so this pair that's now holding the nucleophile on is the one that came from the nucleophile. This pair that was holding the halogen on is now the one that ends up on the halogen. So a negative replaces a negative. The neutral molecule becomes a neutral molecule. So here are some of the possible negative nucleophiles. There are others, but these are the main types. And so you can imagine what would happen if we replaced the X with each of these things. So replace the X with an iodine, you get an alkyl iodide. Replace the X with an OH, you get an alcohol. Replace the X with a cyanide, you get what's called a nitrile. You replace the X with an alkynyl group, and you get an alkyne. Replace the X with this, OCH2CH3, what do you get? Well, a carbon group on an oxygen with another carbon group, that's an ether, and so you can make ethers this way. or we can make thiols, or we can make what are called sulfides. So an R bonded to an S bonded to a methyl group, that would be what's called a sulfide, 2 carbon groups on a sulfur, analogous to an ether. So what I want you to do is draw the products of each of these reactions. Notice the reagent written a little bit differently in some of these. This one written sodium hydroxide, but you know that it's actually a sodium positive and a negative hydroxide, and it's the negative hydroxide that's the actual nucleophile. Same thing here, same idea. In this one I've just written the negative without worrying about what the positive is, so it's sort of a net ionic equation. In this case I've written the negative not over the arrow, but as another reagent on the left-hand side. Means the same thing. And the last one shows both the potassium and the SH, but you know that that's actually an SH minus. So go ahead and stop the video, write down the product in each case. Okay, so here are the answers. First one, we replace the bromine with a hydroxide. It becomes a neutral alcohol. Pretty simple, just replace the bromine with an OH. Second one, we're going to replace the chlorine with an iodide, and so instead of ethyl chloride, we get ethyl iodide. Third one, we're replacing the bromine with a cyanide, and so it becomes what's called a nitrile. That is a C triple bond N molecule called a nitrile. In the fourth one, we're replacing iodine with a negative oxygen. Now notice I have to turn it around so the oxygen is what becomes attached to this carbon in place of the iodine. So there's that oxygen, and then the CH2, CH2, CH3, CH2, CH2, CH3, and so this product is an ether. In this case, we're replacing the chlorine with the SCH3 group, and it becomes a sulfide. As I mentioned, a sulfur with 2 carbon groups is what's called a sulfide. And in the last case, we replace the bromine with an SH minus, so it becomes a neutral SH. We call that a thiol. So that's the first category, negative nucleophiles. Neutral nucleophiles, that is the ones that don't have any charge, like water, for example, when it replaces a halogen, because the nucleophile itself is neutral, it has to become positive in the final product, because it's essentially giving away a pair of electrons in order to form a bond with that carbon, and the halide is leaving with a negative. So if the halide is negative, the other product must be positive to keep a net zero charge. So this is a net zero charge on this side and a net zero charge on this side. So here are some main types of neutral nucleophiles we will see. There's a series of different amines. Ammonia itself has 3 hydrogens. This is called a primary amine. It has 1 carbon group and 2 hydrogens. Again, 3 bonds to nitrogen. This is a secondary amine. It has 2 carbon groups and 1 hydrogen. And by the way, those 2 carbon groups don't have to be the same as each other. They often are, but they don't have to be. So that's what's called a secondary amine, 2 carbon groups and a hydrogen. And then this is a tertiary amine, 3 carbon groups and no hydrogens. In each case, the nitrogen has a total of 3 bonds. These are amines, and we've talked about those before. And again, just to be clear, these 3 R groups don't have to be the same as each other. They may all 3 be the same. You may have 2 out of the 3 be the same and the third one different, or all 3 of them may be different. But those all basically react in the same way. And then there's the oxygen nucleophiles, neutral, which are water and alcohols. Again, they're very similar to each other. The oxygen has 2 bonds and 2 lone pairs in both cases. In this case, the 2 bonds are a hydrogen. In this case, 1 bonds to a hydrogen and 1 bonds to an R group. 2 subcategories under the neutral nucleophile. So to be clear, we had negative nucleophiles. They all react in essentially the same way. Neutral nucleophiles, there's 2 subcategories because they react a little bit differently. There's ammonia and the amines, which I'm going to call nitrogen nucleophiles. And then there's water and alcohols, which I'm going to call oxygen nucleophiles. These react a little bit different from these. So when ammonia, or an amine, reacts with an alkyl halide, the nitrogen with its 3 groups, whether they're hydrogens or carbon groups or some combination, simply replaces the halogen. So here's the nitrogen with the 3 groups that it had, still there, but now it's got a 4th group, which is the R group from the halide. So essentially this has come in attached to the carbon group, and the halide is left with its pair of electrons. So it becomes negative, which is handy because now a nitrogen with 4 bonds becomes positive. And so that's the final product. It's an ionic compound with what's called an ammonium ion, nitrogen with 4 bonds and a positive charge. The counter ion for that is then the negative halide that came off from the alkyl halide. So it's really all one reaction, but we can write it depending upon how many groups were on the nitrogen. So if the nitrogen had 3 hydrogens, once the reaction is done, it still has 3 hydrogens. Now it's got the R group, so for a total of 4 bonds, and so it's positive. If the nitrogen had 1 R group and 2 hydrogens, and we had another R group from the alkyl halide, now it has 2 R groups and 2 hydrogens. Again, a positive nitrogen, because it has 4 bonds. If there were 2 R groups and 1 hydrogen there, and we had another R group, now it has 3 R groups and 1 hydrogen, so a total of 4 bonds for a positive charge. Or if the nitrogen had 3 R groups to begin with, we add another one from the alkyl halide. Now it has 4 R groups, so the nitrogen literally has 4 different carbon groups on it, 4 bonds of nitrogen, again, positive. And in each case, then the halide is the counterion for that positive charge. So in each case, we're starting with a neutral molecule and we're getting an ammonium ion. This ammonia has no R groups. It ends up with 1, so it's now a primary ammonium ion. If you start with a primary amine, now it has 2, so it's a secondary ammonium ion. If it's secondary amine to start with, it picks up 1, becomes a tertiary ammonium ion. And if it has 3 R groups to begin with, so it's tertiary amine, now it has 4, so it's called a quaternary ammonium ion. So basically you're just adding an R group to the nitrogen, and it's going from no R groups to 1, so primary. A primary becomes secondary, a secondary becomes tertiary, and a tertiary becomes quaternary. That's the nitrogen nucleophiles. Here are some examples. So what I want you to do again is stop the video and see if you can write down what would the product be when we react N-propyl bromide with ammonia. We get N-propyl ammonium bromide. The 3 hydrogens that were on there are still there. Nitrogen becomes positive, and the bromide is the counterion for that. If we take dimethylamine, which has 2 carbon groups and 1 hydrogen, we add another carbon group from the alkyl chloride, we now have 3 carbon groups, the 2 methyls that were originally there, and the ethyl group. The nitrogen, of course, now has 4 bonds, so it becomes positive, just as this nitrogen had 4 bonds, and it became positive. And the counterion for that positive is now the negative chloride that was on the ethyl chloride to begin with. So we have dimethyl ethyl ammonium chloride. Notice that this was a secondary amine, now it's a tertiary ammonium ion. If we started with a primary amine and we had another carbon group, that carbon group is now attached to it, and the N-propyl group from the amine is there. So a primary amine becomes a secondary ammonium ion. Notice that these 2 groups aren't the same as each other. They could have been. If this alkyl group was the same as this alkyl group, then these would both be the same. But they're not, so we have a secondary ammonium ion. Again, a primary amine becomes a secondary ammonium ion. And in the last case, a tertiary amine, in this case all 3 methyl groups, adds another methyl group from the methyl iodide, and now we have 4 methyl groups on the nitrogen with a positive charge. So that's a quaternary ammonium ion, and the iodide is a counter ion for that. So that would actually be called tetramethyl ammonium iodide. So that takes care of the neutral nitrogen nucleophiles, ammonia, and the amines. We saw how they react to form ammonium ions. Now let's look at the neutral oxygen nucleophiles, specifically water, and alcohols like methanol, ethanol, isopropyl alcohol, and so on. So what happens is that, just like with ammonia and the amines, this molecule with a pair of electrons is going to replace the halogen, and it totally replaces it. In other words, the whole water molecule is now attached there, and because there are now 3 bonds on that oxygen, it has a positive charge. We've seen lots of 3-bonded oxygens before, specifically H3O+. But how does that happen? Well, essentially the oxygen shares a pair of electrons that it had to itself before, and so electronically it's giving away 1 electron, and so it becomes positive. And of course the halogen that is left takes both of its electrons with it, and so in essence gains 1 electron, and so it becomes negative. Same thing happens with an alcohol. It shares a pair of electrons with the carbon. The halogen leaves with its pair of electrons, so it becomes negative. The alcohol that was part of the alcohol now has 3 bonds to it, and it has 1 pair of electrons, and so therefore it's positive. We've seen those lots of times. So this set of reactions is really just like with ammonia and the amines, in that you get a protonated alcohol or a protonated ether instead of an ammonium ion. The difference, though, is this. These molecules with a positive charge on oxygen and an extra hydrogen, those are very strong acids. So they're going to give away an H plus if they can to anything that happens to be around, whether it's the water solvent that it happens to be in, or in this case an X minus that picks up the extra H plus and becomes HX. Now that's itself a strong acid, and it's going to want to protonate something if it can. But to keep things balanced equation-wise, we write that as HX. So we figure it's the X minus that's going to pull out that H plus. The point is, this loses an H plus. Same thing here, that hydrogen very acidic, it loses its H plus, and we write HX as the byproduct. So alkyl halides plus water give alcohols. Alkyl halides plus alcohols give ethers. Here's the sort of good generic Lewis dot structure formulation. as I said before, the alcohol or water, depending upon what that group is right there, donates a pair of electrons in here, forms a bond with that R group. This is a new bond. In so doing, it essentially gives away one of the two electrons it had before and becomes a +1 formal charge. And at the same time, this pair of electrons that was shared between the carbon and the halogen go off onto the halogen by itself. That's this pair right here. And in so doing, it gains one electron and it becomes negative. And so we end up with this ionic compound of a protonated oxygen with a halide. And as I said, and indicated by the brackets on this molecule, this doesn't last. That then immediately protonates it onto the halide and it becomes HX. And what you end up with then is a neutral molecule which has an extra R group that this did not have before. So again, if this was water, it becomes an alcohol. If this was an alcohol, it becomes an ether. And again, just to be clear, the difference between nitrogen nucleophiles and oxygen nucleophiles is the product of an oxygen nucleophile is a strong acid and gives away an H+ in a subsequent step. Now, let's do some examples. So, as usual, I'm going to ask you to stop the video and write down the product of each of these reactions. So again, it's an alkyl halide of some sort with an alcohol or water in each case. I'm going to ask you to write down the product after it loses its H+, which is what you would actually do on a test or a quiz. So, as I said, stop the video and write down the structures. So in this case, the bromine gets replaced by the water, which then loses an H+, and you just get an OH on there. So alkyl halides plus water give alcohols. Here the halide gets replaced by the whole OCH2CH3 group, and so we end up with an ether. Again, that hydrogen was on there initially, but then gets lost, and the byproduct here would be HCl. It's not written because this is not a balanced equation. In this case, the OR group, this whole thing is the R group, replaces the halogen. So here is the CH3, CH2, CH2 chlorine, CH3, CH2, CH2 oxygen, and then the group that was on the oxygen is still there. The hydrogen that was on here initially would have been on this oxygen, but it gets lost, and so you end up with a neutral ether in that case. Same idea here, the iodine gets replaced by the methanol, but then it loses its H+, and you end up with a methoxy group on that same carbon. That's the end of the lecture. Thank you for your attention.